All right. It's my pleasure to introduce Ed Richmond, who will talk to us about the isomorphism problem for Schubert varieties.
Hi, guys. Well, first off, I want to say thanks for the invitation to speak. I have to apologize for not being able to attend. I was really looking forward to catching up with a lot of you who I haven't seen in several years. But I am thankful that I'm at least able to participate remotely, and I can share some work that I've been doing on the isomorphism problem for Schubert varieties. Okay, so I should mention that this is joint work on two separate projects. The first one is with William Slofstra at Waterloo, where we look at this problem for Schubert varieties coming from complete flag varieties. And then the second project was with Mihail Taragachi and Weihong Zhu. I believe Weihong gave a short talk last night at the conference, where we look at the same problem for the class of co-minuscule Schubert varieties. And this talk is going to involve both of these projects, but they are separate projects. Okay. All right, there we go. Okay, so I mean, this is a workshop on Schubert varieties, so I'm sure people have seen this slide many times before. So we're going to let G be a reductive linear algebraic group over C, and we're going to set a Borel. We're going to let we're going to let P denote some parabola containing B, and W the Weyl group of G. The partial flag variety G mod P has a Bruja decomposition into B orbits. These B orbits are indexed by these cosets of the Weyl group, W mod W intersect P. And instead of saying cosets, it's very common for us to take minimal length coset representatives. So we'll let W upper P be this set. And the Schubert variety is basically you take one of these orbits, indexed by a minimal length coset representative, you close it up, and there you have it, the Schubert variety. And the question we're going to be dealing with today, or at least for this talk this morning, is given two Schubert varieties, one in one flag variety and one in another, when are these Schubert varieties algebraically isomorphic? This question is a very classical question from algebraic geometry. You have two varieties. You want to be able to tell whether they're the same or different algebraically. Okay, so I wanted to sort of give an outline of kind of some things that are guaranteed to happen if you do have two isomorphic Schubert varieties. Well, first things first is that the lengths of the corresponding Weyl group elements have to be the same. This is just because, this is just the complex dimension of these varieties. Maybe a little bit less obvious is that these, when you look at the Bruja intervals, that these have to be poset isomorphic with each other. And then other things like, for example, if you look at cohomology rings or Chow groups, if you have an algebraic isomorphism, then all of these things have to be either group isomorphic or ring isomorphic. But the sad thing is that in general, none of these properties are going to be sufficient to determine algebraic isomorphism. There are many examples where all of these things perfectly match between two Schubert varieties, and they're not isomorphic. So the question is, how do we resolve these things? So in this talk, we'll discuss two cases. The first case, as I mentioned before, is work with William Slofstra, where we're going to look at complete flag varieties, where the parabolics we're going to take are just going to be the Borels themselves. This is the complete flag variety. And then the second case we're going to look at later is going to be co-minuscule flag varieties, where the parabolics that we're going to be taking are going to be certain maximal parabolics that satisfy some extra conditions. Now, I'm not the only one that has thought about this problem, so I'd like to mention some other results on the isomorphism problem. So back in 2007, Devlin, Martin, and Reiner looked at a certain class of Schubert varieties coming from the complete flag variety of type A. They call them partition Schubert varieties. They're a certain class of smooth Schubert varieties, and they were able to prove for this certain smooth class that Schubert varieties were isomorphic if and only if their cohomology rings were ring isomorphic. So this is a very nice result. This is probably the earliest result I could find that sort of gave a serious sort of look at this problem of isomorphisms. The second result right here is sort of somewhat indirect. Torque manifolds were determined to be are determined by equivariant cohomology. This is the result of Masuda in 2008, where if you have two torque manifolds, that basically they have to be algebraically isomorphic if their torus equivariant cohomologies are the same. So this doesn't, torque manifolds aren't always Schubert varieties, but some of them are. There's a later result by Karapuchami that says that a Schubert variety is toric if and only if its indexing element is a Coxeter element, which just means that it's a product of distinct reflections. So this gives some sort of a classification of isomorphism classes for these toric Schubert varieties. And then much more recently, last year, my co-authors on the second project, Taragashi and Zhu, proved that for the Grassmannian, this is type A where P is maximal. In this case, we can index Schubert varieties by partitions, and that two Schubert varieties in a Grassmannian are going to be isomorphic if and only if their corresponding partitions are the same up to transpose, which was a very nice result. So these are the things that I could find. There may be more out there, but these are the ones I'm going to mention now. Okay. So I'd like to talk about the complete flag variety case. And before I can do this, I want to talk about some of the combinatorial data because the characterization that I'm looking for is going to be combinatorial in nature. Given a complete flag variety or you know a group and a Borel subgroup, we're going to consider the simple roots and simple co-roots living in the Cartan subalgebra and its dual. And we're going to define the Cartan matrix of G just to be the n by n matrix A, where these matrix entries are just simply the roots evaluated at co-roots. I'm going to give some examples. If you're not familiar with this, then I'm going to give some examples in a little bit. But Cartan matrices of Lie groups are, you know, you can find a list of them on Wikipedia or Bourbaki. So these aren't very mysterious things. Okay, so one thing that's true is that the Weil group is generated by a set that has a generating set of simple reflections, and this set of reflection is going to be in bijection with the number of simple roots or co-roots. So if I have alpha 1 through alpha n here, I'm going to have an S1 through Sn here, and the Weil group is a Coxeter group that comes equipped with a Bruja partial order and a length function. Okay. By the way, if any of you guys have questions, just feel free to interrupt, and you know, I'm happy to take questions at any time. Okay, so some examples. So here's some classic examples. We can take G to be special linear group. SL4, this is type A3. It has 3 generators, 3 simple roots, and if you look at this matrix, you know, this is just ordered rows going top to bottom and left to right, you know, 1, 2, 3. The Cartan matrix is just simply given by these numbers. Some things to note is that the diagonal entries in the Cartan matrix are always 2, and the off-diagonal entries are always non-positive. And if you have a 0 entry, its transpose entry also must be 0. The Weil group in this case is just permutations on S4. Another example, you could take a look at the symplectic group SP4. It only has 2 generators, and here you can see, you know, this is not a symmetric matrix, which is fine. Cartan matrices don't need to be symmetric. And the Weil group in this case is the dihedral group on 8 elements. Okay, I know I've already defined Schubert variety, but I'm going to define it again. This time, since we're looking at the complete flag variety case, I'm going to drop P completely from the picture. But I am going to introduce this this notation A, where a Schubert variety will be indexed by W, and the Cartan matrix A. This is a little bit sketchy in the sense that every G uniquely determines a Cartan matrix, but not every. But there can be several different G's that have the same Cartan matrix. So there's this sort of tricky, like these aren't necessarily in one-to-one correspondence, but when you're dealing with flag varieties and Schubert varieties, this is actually okay. It's okay to sort of have consider the Cartan data versus the group when considering these Schubert varieties. And now the question is going to be, given a Schubert variety of one type, given a Schubert variety of another type, they're going to have corresponding Cartan matrices. When are these things going to be algebraically isomorphic? Okay, so let's look at some low-dimensional cases of this problem. So if the length of W is just 1, then W is just equal to just some simple reflection, and it turns out that all of these one-dimensional Schubert varieties are just projective space. So when it comes to the isomorphism problem, all one-dimensional Schubert varieties in the complete flag variety are the same. They're just projective space, and we're done. So this is sort of case 0 in a lot of ways. Things get more interesting when you go to two-dimensional Schubert varieties. Here, W is going to be equal to some product of two simple reflections, Si times Sj, where I and J are not the same. It turns out that Schubert varieties in this cases are just Hertzsprung surfaces. So they're smooth varieties. In particular, they're going to be some P1 bundle over another P1, where you have this sort of indexing integer n. This n is going to correspond to some twist in the fiber when you look at this this P1 bundle over P1. But in terms of the Cartan data, it's actually quite easy to sort of extract what this n could be in relation to Si times Sj. N is just going to be this negative Aij. So this is something that with just a little bit of work you can see. Basically, Hertzsprung surfaces, in terms of their algebraic isomorphism classes, are indexed by positive, or I should say, non-negative integers. They can be 0. So in this case, if I have two-dimensional Schubert varieties, one given by I and J, the other one given by K and L, then they're going to be isomorphic. They're going to give you the same Hertzsprung surface if and only if the corresponding Cartan entries, Aij and AKL, are going to be the same, which is pretty nice. One thing I'd like to observe is that when you look at this characterization, there's no dependence on the transpose entries. And that's because W equaling Sj, Si in the reverse order is potentially a different Schubert variety. You just can't simply swap these two and expect to get the same thing. And if I swapped I and J, then the dependency is going to be on the transpose entry. Okay. All right. So I want to give a quick definition to sort of lead into my next slide. So one thing that's going to be really important is the simple reflections that appear in any reduced word of W. So I'm going to define the support of W to be just this. It's just going to be all simple reflections that are less than W in Brouwer order. This is just basically saying, all the generators you need to write out W as a reduced word. And this is going to be important. Taking this two-dimensional example, I'd like to give a definition of Cartan equivalence. So this is right now just purely combinatorial. We're going to say a pair WA and W prime A prime are Cartan equivalent if there's a bijection between their supports, sigma, such that the following two things happen. First, there has to exist there. You can take W, you write out a reduced word. There has to exist a reduced word. Oh, was there? heard some commotion in the room. I wasn't sure if that was a question or just nothing. Okay, sounds good. You find a reduced word of W such that when you apply you apply sigma, this just happens to be a reduced word of W prime. So this is very lucky to sort of have this happen. Let's say you do this happen, but this is not quite enough. The second thing that needs to happen is that for every J and K, or J less than K, when you look at the corresponding Cartan entry in A, that this has to match perfectly on the other side. And this has to happen for all pairs J and K, like this. So let's look at an example. Let's take W to be 1, 2, 1, 4, and W prime to be 5, 4, 5, 1. Let's say they're both type A. And I claim that, if I look at this sequence and I map it to this, so the supports of the first one is just 1, 2, and 4. The support of the second one is 1, 4, 5. And if I map S1 to S5, S2 to S4, and S4 to S1, I claim that this is a Cartan equivalence. First of all, this mapping sends this reduced word exactly to this reduced word. And if you know something about type A, these are both clearly reduced. So part one is satisfied. And then for part two, one thing to know about these, since we're dealing with type A, if two numbers are adjacent, then A is -1. And if they're the same, then it's +2. And if they're farther apart, then it's 0. And you can see that basically, when I look at pairs, adjacent entries will map to adjacent entries, far apart entries map to far apart entries, and matching entries will map to matching entries when you look at this order. So, and basically, like in spirit, what I have here is, I have this sort of longest word of, A2, and then I have this sort of, this commuting generator attached on the end, and in spirit, I basically have the same thing on this side. So this is a Cartan equivalence. You have to prove that it's equivalence relation. It's not trivial, but it's not super difficult either. And here's the theorem. Turns out that this condition of Cartan equivalence is exactly what we need for the isomorphism problem for G mod B. So we're going to let given Schubert varieties XWA and XW prime A prime, the following are equivalent. First, the pairs are Cartan equivalent. That's part one. Part two is our goal. Schubert varieties are algebraically isomorphic. And then part three is not just a bonus, it's actually necessary in the proof that we have. And this sort of relates back to some of the cohomological conditions that we saw before. There exists a graded ring isomorphism between the cohomologies, but it can't just be a ring isomorphism. It has to be one that maps the Schubert classes of this ring to the Schubert classes of this ring. And it has to be on the nose. It can't be scales. It can't be linear combinations. It has to be, there's sort of, a unique set of Schubert classes over here. And it has to, and this map phi has to map them perfectly onto Schubert classes over on the other side. And it turns out these three things are equivalent. A couple of remarks about this theorem is that first, when in our paper, in my paper with William, we actually did this at the Kac-Moody level. Kac-Moody flag varieties are certain infinite dimensional generalizations of flag varieties, but they have finite dimensional Schubert varieties. It includes flag varieties of affine type and finite type, but then it also includes, classes of flag varieties, never seen by humans before. It's sort of there's a lot of wilderness when dealing with Kac-Moody flag varieties. So this is particularly nice. One thing to note, one comment about condition 3, it's definitely possible to have ring isomorphism between cohomology rings that do not preserve Schubert classes. So for a while, I was hoping that I could drop this preserve Schubert classes portion, but there's an immediate counterexample when dealing with Hertzsprung surfaces in the sense that Hertzberg surfaces, are algebraically indexed by n, but if you look at them diffeomorphically, they're actually diffeomorphic up to parity. Basically, is n odd or even? And it only has two classes. And if two varieties are diffeomorphic, then they're going to be homeomorphic topologically. So cohomologies are going to be the same. You basically only get two different types of cohomology rings, for one for odd and one for even. And sure enough, when you look at it closely, you can certainly cook up an isomorphism between, let's say the Hertzberg surface indexed by 1 and by 3. These are actually the two two-dimensional Schubert varieties in G2 mod B. And you just play a game, you just send Schubert classes to, the right linear combination of the other Schubert classes, and it magically becomes a ring isomorphism. So this condition about preserving Schubert classes is super important in this theorem. And the spirit of this theorem is basically that Schubert varieties are algebraically diverse. And what I mean by this is basically like if you happen to be given two Schubert varieties and they happen to be isomorphic, then they're going to be isomorphic in a pretty obvious or a fairly trivial way. Basically like if you're given two random ones, then chances are they're going to be different. And I'm not going to talk about this much, but for example, I've been looking at sort of the sizes of isomorphism classes in type A, and I would say that most isomorphism classes in type A are either of size 1 or size 2. So it's so the isomorphism classes get quite small. Okay. So let's look at some examples of this theorem in action. So here I have A3 and B3. They're given by these Cartan matrices, and I just dropped the primes, and I'm also slightly abusing, I'm using the type to indicate the matrix. But for example, if I'm going to look at the Schubert variety indexed by S1, S2, S3, this is a unique reduced decomposition. And I look at the same thing on the other side. If I map 1 to 1, 2 to 2, and 3 to 3, this turns out to be a Cartan equivalence because the Cartan entries that are involved in this upper corner, this upper triangle corner, basically -1, 0, and -1, and it just happens to match on the other side. However, if I reverse these, if I do 3, 2, 1 versus 3, 2, 1, there's no way I can construct a Cartan equivalence between these two. First, these reduced words are again unique, so there's no choice but to send 3 to 3, 2 to 2, and 1 to 1. But then, of course, now I'm dealing with the lower triangular portion, and here, type A, the upper and lower, this is symmetric, so they're the same, but B3 is not symmetric, so there's no way these can be isomorphic. And these facts are not new. This wasn't something I discovered. You could, if you understand these flag varieties and Schubert varieties geometrically, then there are other reasons for these to be isomorphic and these to not be isomorphic. Another interesting note from Cartan equivalence is that if I restrict to type A and if I look at S2, S1, S3, and I compare it to its inverse, S1, S3, S2. So 1 and 3 commute. So I'm basically putting 2 on either side. These are inverses of each other. And after, a few minutes of thinking about it, you can see that there's no way to construct a Cartan equivalence between these two elements. And what this is saying is that a Schubert variety is not indexed by W is not necessarily isomorphic to the Schubert variety indexed by its inverse. Which is something I actually thought was true for a little while, but but now after working on this, I realized this is almost never true. But W and W inverse share a lot of the same combinatorial properties. They have the same Brouwer interval, they have the same number of reduced words. They have a lot of things they have a ton of things in common. If one's smooth, the other one's smooth. Basically, a lot of the local properties of one transfer to local properties of the other, but when you try and pass the global things, then things can fall apart. I was also able to verify this separately, independently, that these two Schubert varieties are not isomorphic. So this was something that I thought was like, the Cartan equivalence gives an easy way to sort of see this. So some, see, I'm doing, okay, yeah. Okay, so just a few words on the proof. I know it's the last day of the conference, and sometimes proofs given in 3 minutes are a little tough to digest, but let me just kind of give you the spirit of what's going on. So the proof is basically 1 implies 2, 2 implies 3, 3 implies 1. And for the first part, basically what we're doing is we're doing some representation theory. We're going to try and find a highest weight module such that our flag varieties map to this height weight module. And then what you do is you look at these corresponding Schubert varieties that are sitting inside these flag varieties. And the fact that we have a Cartan equivalence allows us to find such a module such that basically these maps remain injective when restricted to the Schubert variety on either side, and that their images map perfectly onto what they are in this PV. Now these maps don't have to be well behaved on the flag variety level. They just have to be behaved well enough on the Schubert variety. And the Cartan equivalence is exactly what you need to sort of guarantee this. And then what you get then is you get an algebraic bijection between these two Schubert varieties. And since Schubert varieties are normal, it's a result of Zariski's main theorem that algebraic bijections are actually algebraic isomorphisms. Okay, so that's 1 implies 2. For 2 implies 3, this one is short. Basically, if you have an algebraic isomorphism, it's well known that the effective cone in the Chow group is spanned by the minimal extremal rays of the effective cone are spanned by Schubert classes. This is a result of Fulton, McPherson, Sotile, and Sturmfels in '95. I write Kumar and Nori here because they had an analogous result in the sort of in-variety Kac-Moody setting, which is what we needed in our proofs. But basically, this is saying that if you have an algebraic isomorphism, you look at the corresponding map on cohomology. So effective cone has to map to effective cone. So therefore, the Schubert classes have to map to Schubert classes. And then for the last direction, so now you have this map on cohomology, and you want to construct a Cartan equivalence. And then this is basically, a very intense exercise in Schubert calculus, in particular using Chevalet's formula to say like, okay, I have this map. I'm going to use Chevalet's formula to sort of slowly build up all the combinatorial structure of W, and prove that the map on cohomology that we have that identifies Schubert classes can be used to actually construct a Cartan equivalence, and that actually does take quite a bit of work and is quite technical. But there it is. So you have so this is kind of what we do. Any questions? Yeah, so it's a little bit of cheating in this sense. So you look at this Cartan matrix, and you look at the entries. Okay, so I guess step 1 is so you're given this Schubert variety, and so we're dealing with this on the Kac-Moody level now. So this is kind of my thinking. And so the Kac-Moody flag variety is sort of built out of the Cartan matrix. Cartan matrix is where we start. So basically we need to find a weight that's big enough. So we have this Cartan equivalence. Sorry, I haven't thought about this question in a little while, so I'm kind of rambling a little bit. That basically, like, so this is what we know. We know that we have this W, and we have these entries of A that sort of correspond to W, and then we have W prime and A prime, and we know that since we have a Cartan equivalence that these numbers match. These numbers match. on both sides. So then what we do is we build an A double prime. So that basically, so this A and this A prime may not be compatible, but what you can do is you can sort of change your G, and you can change your G prime such that the same Schubert variety appears in a slightly different flag variety, indexed by A double prime. And then you just have to pick a lambda. You need to pick a lambda highest weight that basically sees all the Cartan data that you need. So one danger is that if you pick V too small, that the variety structure on your flag variety and on your Schubert variety could become degenerate. Like, it has to be big enough. So there's something called the stable variety structure of Kumar, and so step one is kind of like, make sure there's some compatibility between A prime and A double prime, and then the second step is to pick lambda large enough that the stable variety structure is realized. Basically you pick this highest weight, and then I think there's this technique where there's this natural, you get this sort of this natural map from the flag variety here, and this map may not be injective, but you know that it's going to be injective when you restrict to the Schubert variety. That wasn't a great explanation, but I don't know if that was sufficient for now. Okay. How do you define the Schubert classes? You define them to be the minimal rays of the effective cone. And then oh, I see. I see. Yeah. So you mean the cohomology of the Schubert variety? Yeah. So we define them to be, so you have homology classes, and you define them to be just the Kronecker duals. So there's no, so Schubert varieties are singular. So there's no Poincare duality. So you use the Kronecker dual. You use like the sort of classic Kronecker dual classes. Yeah, and this is kind of standard in the Katz-Moody, because in the Katz-Moody setting, there's the flag variety is infinite dimensional, so you have nothing on the other side that's finite dimensional to work with. So you use Kronecker dual classes for the Schubert classes in this case. Okay. Yeah, they're finite codimension classes, but they kind of they don't see each other. And like, if you go up, you go up forever, and you go down forever, and they never meet in the middle. So we just ignored. Yeah, so so those finite codimension ones, this is not a result about those finite codimension ones. Yeah, this is about the finite dimensional ones coming from the bottom. Oh, sorry. That I couldn't. What was the computer question? Yeah, exactly. This is the in variety cell decomposition, where you sort of grow it from the bottom, and then you take a limit. Yeah. So some comments. So I'm going to switch to talking about the cominuscule case in just a second. So I want to mention that when you attempt to use Cartan equivalence for the partial flag variety case, that basically, as it stands on its own, it's neither necessary or sufficient. So one thing that's quite clear is that so W is obviously Cartan equivalent to itself, but if you just put a P up here, then it's almost never the case that these two Schubert varieties are going to be algebraically isomorphic. There are plenty of cases where, in fact, one of these is singular and one of these is smooth. So obviously there has to be some involvement in P if you're going to modify Cartan equivalence. But conversely, you can certainly have here I have a partial flag variety case of type A and type C. This is kind of technical. What these Schubert varieties are, what this type A one, all this is right here is this is the Grassmannian of one planes in C4. So this is CP3. And the second one right here are isotropic lines in C4, where the isotropy is taken with respect to a symplectic inner product. But it's well known that, you know, isotropic lines, that every line is isotropic with respect to a symplectic inner product. So this is sort of the isotropic Grassmannian lines in C4. This is just the regular lines in C4. These are obviously the same. They're both CP3. But there's no way that these can be Cartan equivalent. In fact, the support sets of these two Schubert varieties are different. This is 1, 2, 3. This is 1, 2, 1. And you know, so Cartan equivalence, there can be things where, like, you know, Cartan equivalence doesn't have a chance, but, you know, things can become isomorphic. I do have some ideas, I should quantify, you know, some extremely unvetted ideas of how I could modify this, but, you know, I really haven't tested anything out. But, you know, but this is just to let you know that, you know, this partial flag variety case, you know, when you're modding out by this larger parabolic, that, you know, strange occurrences can happen. Okay. So which brings me to the, were there any other? Oh, sorry, I couldn't hear you very well. Yeah, yeah. 2 is equivalent to 3. Yeah, so this is part of my idea. You know, somehow, you know, so the braid here, so the type C braid here, you know, needs to be 4 long before it happens. So somehow this is like this S1 and this S1 are kind of not, they're not seeing each other because the braid is not complete. And somehow this is like, yeah, I don't know. So to be honest, I haven't thought about this in a little while, but, you know, but I feel like there could be some adjustments that could be made to accommodate this situation. And then the question would be, you know, is that all that can happen, you know? But yeah, but I haven't thought about it in a little while. One is equivalent to two, yeah, there exists a reduced word. But it turns out that Cartan equivalence will give a bijection between the set of reduced words of one and the set of reduced words of the other. Mhm. Yeah. Sorry, it was difficult for me to hear that. I see. I see. Well, okay. So it turns out that, okay, so here's the reduced word. So we say there exists a reduced word, but it turns out that if you have two things that are Cartan equivalent, that I could actually put any reduced word here. And by the way, it's okay. It's a little tricky because Cartan equivalence, like the map sigma, is not necessarily unique. For example, you know, I could braid 5 and 4 here, and I can send S1 to S4 and S2 to S5, and that's another Cartan equivalence. That's totally fine. But when you think about all the reduced words here, so this S4 can move anywhere, and then this 1 and 2 can braid, and by the same thing here, you can see that basically, any reduced word I cook up here, there's going to be an analogous reduced word on the other side. Yeah. This just shows you the strength. So 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 one thing, they didn't say there's all, but one thing is like if you have two things that are Cartan equivalent, the number of reduced words on one side is going to be the same as the number of reduced words on the other side. Yeah, because just like when I look at these two, I can it's easy to reason that the number of reduced words is the same on both sides, and that you can. The only things that don't give Cartan equivalence is if I choose to move this 4 to the middle, then I have to move the 1 to the middle to sort of match it. So there is some sort of you can't just match any reduced word with any reduced word, but they are kind of matching in a lot of ways. Okay. All right, so I'd like to move on to the partial flag variety case that we do know something about, and that's going to be co-minuscule flag varieties. So I'm kind of starting over a little bit with this portion. So we're going to let R be the root system of G, and the root system decomposes into positive and negative roots, and we have simple roots. And again, the simple roots correspond to the generators of the Weil group. I'm indexing by alpha instead of I in this case. And for any subset of generators, we have a parabolic subgroup, PJ, which is just given by this, this double orbit by B of the Weil group generated by J. And we're going to say a flag variety is co-minuscule if there exists a simple root gamma such that the following two things happens. First, J has to be maximal proper. That J has to sort of comprise everything of S except this single root. And that this sort of distinguished root gamma appears with coefficient 1 in the longest root of the positive roots. And we're going to call gamma the co-minuscule root of the flag variety. And we're gonna sort of index P by this root. Let me go to the next slide. So in this case, I'm sort of restricting to only flag varieties of finite type. And, there's only so many given the classification. So here's the classification of co-minuscule flag varieties. So the Grassmannian, every root is a co-minuscule root. So I can pick any of these alpha 1 up to alpha n. In type B, you can pick alpha 1. That's a co-minuscule root, and you get odd quadrics. In type C, you can pick the last root n that gives you the Lagrangian Grassmannian. In type D, you have three options. You can pick alpha 1, or these sort of, you can pick these leaves basically. On one end, you get the even quadric, so you get both odd and even quadrics. And if you pick either of the nodes on the other end, you get the orthogonal Grassmannian. And then you get these two unusual ones of exceptional type, where you can pick either 1 or 6 for type E6, or you can pick this E7 to get this Freudenthal variety. Okay. And so one nice thing about co-minuscule flag varieties, and I know that several people in the audience have worked with co-minuscule flag varieties, and the general spirit about why people like these so much is that co-minuscule flag varieties are basically just like Grassmannians. They share a lot of similar properties with Grassmannians. For me, one of the biggest things is that, if you work with Schubert varieties in the Grassmannian, we like to index them by partitions compared to Weil group elements. And partitions are much easier to work with in a lot of ways combinatorially. And it turns out that co-minuscule flag varieties also have this sort of partition-like indexing of Schubert varieties, and a lot of the properties just pass over. They're really nice. So to let you know about how we get sort of this partition style indexing set for Schubert varieties, we're going to define the following. So we're going to look at the set of positive roots. And we're going to say one positive root is less than another if their difference is a positive sum of simple roots. I'm not requiring a minus b to be a positive root itself, just that it's a sum of positive simple roots. And then we're going to define, so this puts a poset structure on the set of positive roots. And then we're going to restrict to the set of roots that are all bigger than this distinguished root gamma. So basically this is saying is we're going to look at all alphas that gamma appears in its simple root expansion. Okay, and there's a classic theorem by Bob Proctor that if x is cominuscule, then the poset px is a distributive lattice, just like Young's lattice for Grassmannians, and that there's a bijection between these minimal length coset representatives with lower order ideals in this poset px. And the map is you take your minimal length coset representative and you send it to its inversion set. So the inversion set is basically all positive roots for which then when you act by w, it becomes a negative root, like this. And distributive lattices are very nice. So here's an example. This is this classic Grassmannian. Let's pick out alpha 3 to be our distinguished cominuscule root, and basically the poset p in this case is given by this collection of boxes. So each little box represents a root. This one that I've marked is going to be alpha 3 itself, and basically what you're going to do is for any other box, for example, if I pick this box right here, I'm going to label sort of this hook 1, 2, 3, 4, 5, 6, 7. And what you do is basically you take this box, you look to the left and you look up, and this box will be alpha 2 plus alpha 3 plus alpha 4 plus alpha 5. And that's clearly bigger than alpha 3. Yeah, so the partial order in this case on boxes is going to be, if one box is weakly northwest of the other, then that one's going to be smaller. And when you look at lower order ideals, basically this is sort of going to be sets that are closed under going, up and to the left. You see that you get a Young diagram of a partition. So Proctor's theorem says that basically these shapes are in bijection with minimal length coset representatives W upper P in this cominuscule case, and we get partitions that we like when studying Schubert varieties of the Grassmannian. Now, the nice thing about cominuscule is you just play this exact same game on other types. So, for example, the orthogonal Grassmannian, your bounding shape just becomes slightly different. So instead of getting a rectangle, you get this sort of staircase shape. The roots that contain alpha 7 are given by these boxes, and lower order ideals are these sort of analogs of partition shapes. You just have to be closed. The relation is the same. You just have to be closed under going up and to the left. And these sets form are in bijection with the things that index our Schubert varieties. Here's another example with Cayley plane. You just get different shapes, and it's kind of they're kind of fun to think about. Okay. So in terms of Brouillard order and dimension, a lot of the combinatorial and geometric data of a Schubert variety can be extracted from these posets. So this was sort of the earliest reference of this thing being proved. So Alex, I'm mainly referring to part 1. I think part 2 is just was kind of known just globally. That basically, if you want to think about Brouillard order in W upper P, this just corresponds exactly to containment of diagrams, which is just how Young's lattice works. And that if you want the dimension of a Schubert variety, then you just need to look at the number of boxes. This is super nice. Containment is much easier to see than Brouillard order. A lot of times, I'll stare at two permutations and not know if they're comparable. I can look at two Young diagrams, and know pretty much right away whether they're comparable or not. Notation, instead of using, so from here on out, we're going to index by these lower order ideals. I might just call them partitions, even though they're not technically partitions in other types. So we're going to be using this like x mu. And the result that I mentioned earlier before from Michal Targaci and Weihong Zhu is that for the Grassmannian, they proved that two Schubert varieties are isomorphic if and only if their shapes are the same up to transpose. This is actually equivalent when you think about these poset structures, just that basically, the poset structure needs to be the same. So the partition doesn't need to be the same, but if you transpose the partition, it has the same poset structure on the boxes that are in that partition. So this is sort of a different way of saying what they proved back in 2022. Okay, so the question that I'll be looking at now is like, does this poset structure work for co-minuscule Schubert varieties in general? And the question is not really, because if we're allowed to pair across types, which is what we've been doing, if I look at the poset structure of Lagrangian versus orthogonal Grassmannian, they're going to have the same poset structure. They both give you the same exact shape, like this. So this is an example of two posets being the same, but the corresponding in this case it's the full co-minuscule flag variety. They're not the same. However, we have a fix. What Michal and Weihong and I do is we basically say, okay, well these boxes correspond to roots, and when you're dealing with root systems, they have a notion of long and short root. So what I'm going to do is, if a root is long, I'm just going to leave the box blank, but if a root is short, I'm going to label it with S. So I'm going to look at these. So, and now what I get is, instead of a poset, I get a labeled poset. I get a labeled poset. So updated definition, we're going to let lambda be the poset of inversions labeled by long and short roots. And if I do this labeling, then these are no longer isomorphic as labeled. These are all labeled long. Most of these are labeled short. And here's our theorem. Our theorem says that if I have two co-minuscule Schubert varieties, then the Schubert varieties are going to be algebraically isomorphic if and only if the corresponding inversion sets as labeled posets are the same, which is really nice. So here's some fun examples. I have D5 mod P1 that looks like this. This is what it's. I have lambda given by this lower order ideal. I can look at this thing that's sort of sitting inside E6 as well, and I can see that these are the same, except I have a box coming off here and a box coming off here, and it turns out that these are not the same. These are not the same. So they're not going to be isomorphic. Another example here is B2 mod P1. I have this short root kind of labeled in the middle, and then I can take this sort of this sort of small piece in Lagrangian Grassmannian. These are the same as labeled posets, so these are isomorphic. Okay, some more fun examples. These end up being the same. This is kind of like a line with like a 2x2 box, and then another line of 3 boxes. This is basically the same thing. 3 2x2 box, and then another 3 coming off. These are the same as posets. Here's an example of two Schubert varieties in E6 that are not the same. Good. Okay. So let's see. Was I supposed to end 5 minutes ago, or can I take another 6 minutes? Okay. Okay, so the last thing is basically a word on the proof. I can keep it short. The proof actually uses a lot of the same principles that we use in the complete flag variety case. which is interesting because when you look at the proof of the Grossmanian, the paper that Michal and Wei Hong wrote before this one, the proofs are extremely different, or the techniques are extremely different in that paper. You know, they look at the singular locus of Schubert varieties there just to try and distinguish Schubert varieties. But basically, okay, so let's suppose you have an algebraic isomorphism. We start off with this sort of same foundational result that the minimal extremal rays of the effective cone are the Schubert classes in the Chow group. There's a unique effective generator. Okay, so we're going to suppose Y is isomorphic to some co-minuscule Schubert variety. And then we're just going to apply Chevrolet's formula very carefully. Chevrolet's formula in the co-minuscule case becomes very nice because this is just like a box adding, box deleting operator. Well, okay, so it's a box adding operator, but we sort of reformulate it to be a box deleting operator in our proof. And you can prove that basically, you know, you can put a post-check structure on these extremal rays that basically generates the post set that we want using Chevrolet's formula carefully. And then for the reverse direction, what we do is if you're given two pieces, if you're given two post sets that are, you know, post set isomorphic, then there's sort of this we develop this way of constructing a minimal flag variety. So for example, here, if I'm given this shape right here, we have this technique where we basically we travel along certain chains from this sort of co-minuscule node and generate this sort of minimal flag variety. So for in this case, when I look at this partition, this is sort of the smallest rectangle that this partition fits in. If I have something more complicated like this, I can sort of look at the union of these two chains that are like this, and then I can see that this is sort of the sort of smallest co-minuscule flag variety that this post set can live in. And so then our technique basically is, you know, we're going to take this X lemma, embed it in this sort of minimal co-minuscule flag variety. And then we have a theorem that basically says that if you have isomorphic post sets, then they generate the same minimal minimal flag variety that they embed in, and that and then there's a careful argument you need to say that, you know, that if you identify this isomorphism appropriately, then basically these Schubert varieties land on top of each other. Okay, so that's the proof. Here's some more pictures, and thanks for listening.